talk labs really quick. So first of all, thank you to all of you who filled out the mid-course survey. I looked over the results. Parts were very flattering. You guys are so nice. Parts were just flattering, though. and we can talk about those parts. So, but thank you. I appreciate your candor. So a lot of people felt like, I think, like everyone's like, oh, deep learning is awesome. And pretty much everybody that took time to respond said, and the labs need some help. I think that's like my summary of the mid-course evaluation, which we knew going into this. And so I, again, appreciate your patience. It's totally fine for you to just get mad at me for the labs. I know that they've been, they're not where we would like them to be. So hopefully they'll be much better next year for everyone else. But we're trying hard to make them good for this year for you. So I thought it might be helpful for us to go over the lab spec today for the lab that's due this Friday, spend some time on it, answer any questions, step through things. Sri has done a great job of getting this together. And so I think now's a good time for us just to make sure that the expectations are clear, cover the scaffolding code that's been given, and I'll show you just a little bit about results and things like that. Okay, so this lab is kind of your chance to implement something not quite from scratch, but close to from scratch. We're giving you a little bit of scaffolding code, but not a whole lot. But I think we're giving you the most important bits, and I think we've solved the most important gotchas for you, I hope. So you're implementing improved training of Wasserstein GANs, and so you just have to train the generator and the discriminator. And so the data set is this Celebrity A data set, and you can download it here. There's also some code later on where you can just download it in Colab. There's just three parts in the lab. You implement the generator, you implement the discriminator, and then you implement the training loop. Of those three, the training loop is by far the hardest. It's not too bad. There's a couple of gotchas, and we'll talk about those. So the generator network. Let's first talk about that. So the generator network, in all of our experiments, we've just been using the basic DC GAN generator. And so that's this one right here, 4 convolution layers, followed by some ReLUs. And so we say here, followed by a batch norm. That was true. We started off with a batch norm. Just this morning, Shreya ran an experiment where she took out all the batch norms, and it was faster and it worked better. So I would recommend that you start. An important part of this lab, though, is you actually are allowed, as part of this lab, to implement anything that you'd like to, for both the generator and the discriminator. That's just to give you some flexibility if you want to experiment and have fun. That said, maybe you should just start with what we know works. Okay, so 4 convolution transpose. It follows the exact sizes and everything that are in this paper. At least our reference implementation did. And so let's pull up that figure one more time. Stand by. You remember this figure? So it's just this. Okay? Yes?
What is the 5, like the gray block inside? Is that the kernel size, or?
Yes.
So you have a kernel size of 5, but a stride of 2, and then you need padding to make it the layers go right. The size is gonna double. I guess that kind of doesn't make sense. I guess so. You just need padding for it to go from 4 by 4 to 8 by 8. Or is that incorrect?
So yes, you will need padding, right?
Because you have okay.
You will need padding. Okay. Good. Okay, so I would recommend no batch norms. So this is really, I mean, hopefully at this point you're comfortable enough with PyTorch to know how to do this. Are there any questions about this part? So you'll just create a class. You'll have your forward pass. You can use nn.sequential. Like, shouldn't be too bad. The one question, so the question came up, how do we get things going? We start with a Z that's 100 dimensional. How do we get that into the first shape, into the first 4 by 4 by 1024? The answer is we use a fully connected layer, and then we reshape it. And you all know how to do that. Is that right? Any questions about that? So use the view thing. PyTorch.view. Okay, good. So discriminator network. Again, we used pretty simple, it's pretty straightforward, it just goes the other way. So it looks like the DC GAN architecture. You just go from your input image size, just reduce down, a bunch of convolutions, every now and then stride. But we use leaky ReLUs and a batch norm on the first layer. Actually, again, we didn't use batch norms anywhere in the most recent version. And notice that it just outputs a scalar. So you're going all the way down to a single scalar. Yeah, question?
I think you just answered it, but I'll ask it just to be double sure. So continue to use the batch norms on the discriminator guard except for the first layer, or drop those as well?
Yeah, we drop them and seem to make
Nice,
everything
okay.
better. Yeah. So we're thinking no batch norms
Sweet.
is where you should start. Okay, so finally, the actual training. Yeah.
Sorry, why is that an unconstrained scalar?
Okay, so this is, we didn't really talk about this, but in the original, so you are implementing a paper called the Improved Wasserstein GAN. There was a paper before that called just the Wasserstein GAN. And they're the ones that introduced this notion of a critic. And the critic is a little bit different. It's not outputting the probability, it's just outputting a scalar. And I learned, by the way, it has to do with, you take the, because you guys asked me all these hard questions about the improved Wasserstein GAN. I didn't know the answer, so I went back and I read the papers. So it turns out what they did was they took the Earth mover divergence, which is intractable, and they used this thing called the Kantorovich-Rubinstein duality to transform that into this alternative form. And when you transform it into this alternative form, you get something that's more easily approximatable. But the consequence is that the discriminator just outputs a number. And it's not a probability, it's not a log probability, it's like just a number. Yeah. So that's why they call it a critic rather than a discriminator. Because it's not trying to discriminate two classes, it's just like critiquing the thing, and it's like giving you some feedback. It's just, but that feedback is just a number. Yeah. Kind of weird. Okay, so this is the really tricky bit though. Implement the training algorithm. So you can essentially just follow the pseudocode in the paper. And we've given you some scaffolding code here, which essentially just follows the outline in the paper. Really, the tricky bit is making sure that you reuse variables and making sure that you turn off and on gradients kind of at the appropriate times. That was one of the big gotchas, and so we're just handing that to you. So here's kind of the outline. So for however many epochs you want, you just like load data. So we're also giving you the data loader class. This is the bit that we are giving you as well. So here's where what we do is we say, okay, it's time to train the discriminator. So what we do is we turn on all of the discriminator parameters and say that all the discriminators require gradients. We then go ahead and generate our z, calculate the loss, do the gradient penalty thing, and then eventually call the backwards step, and then eventually take a step. Remember, there's two optimizers now. There's the discriminator optimizer and the generator optimizer. So with the discriminator optimizer, take a step. So we do this for a little while. Then when we're done training the discriminator, we go ahead and turn off all of its gradients. And then we go ahead and do something similar for the generator. And that lets us train one, then the other, then one, then the other. Yes?
So the papers we were looking at last week had it as nested for loops, but this
Yeah.
looks like they're stacked for loops instead.
It's nested.
Okay.
Well, it's nested in the sense that, well, I mean, you take a bunch of steps in the discriminator, and then you take a bunch of steps in the generator.
Okay.
Actually, so it turns out we have learned that we just do one step for the critic. So we actually keep them perfectly balanced, and that seems to work. That seems to work pretty well, given everything else that we've done. I think the thing you'll learn about this lab is Shreya has done a lot of work to figure out the exact combination of parameters that works. If you stray too far from that path, there be dragons there. Just be careful.
So I'm not seeing anything that turns off the parameters for our generator while we're training the discriminator in that pseudocode. Do we do that?
Yeah, I don't know. Shreya, did you?
It didn't seem to matter if I turned it on or not, so I just
Okay.
left it out.
But maybe to be clean, you probably should turn off the generator.
Because we are using generator Yeah, I can try that.
Okay,
It didn't seem to matter though.
okay. Yeah.
Why do you have to turn the gradients off and only store one?
It's not a, no, it's not a memory thing. It's, you only want to train one or the other at a time. So you essentially need to say, because you're going to say something like, so remember when you compose the generator and the discriminator together, if you're not careful, all of those parameters will be adjusted. But that's not what you want. You sort of want the generator has its own loss function, and when you want to update its parameters with respect to its loss function. And the discriminator has its own loss function, which is different. And you want it to update its parameters with respect to its loss function.
Because we use
But they-
we use this discriminator in the generator or something.
We use the generator as a discriminator, yes. So we don't want to push the generator in the direction of the gradient of the discriminator's loss function. Yeah. So probably you should turn it off. But that said, I have run this code myself, and like it seems to work fine. So yeah. Okay, I thought I saw a hand over there. Yeah, go ahead.
I guess kind of along that, isn't like which parameters are being updated just depend on which parameters you pass to the optimizer?
Yes. Yeah, so you can probably set things up really carefully. This is just like extra safe. Okay. Good. So finally, you just need to generate the two images. So they should look something like this. So we found, oh yeah, and then, okay, a couple of hints. These are the parameters that we used. So they're all pretty standard. The one thing to note is we used a pretty big batch size, so 200. Here's some code for downloading the Celebrate A dataset. It's like 1.4 gigabytes, but because it's hosted at Google and you're using Colab, it downloads in like 3 seconds. It's awesome. And then here's a little bit of a dataset class that should help you out. Okay, so I've run this. So we have, like, this is our version of the code over here. And I ran it just this morning. So I ran it for one epoch. And so for us, an epoch is 200 steps. Each step has a batch of size 200. So it's processed 4,000 images. It took, I don't know, 5 minutes or something to do one epoch. And we were getting images that looked kind of like this from the sample. Okay, so you should see results pretty quickly. Now, if you want the really nice results, it's going to take probably more time. But should see some signal quickly.
So would that be acceptable in an image like that? Or what?
No, you should train longer. I mean, we're not going to grade you on the quality of your images because we understand that sometimes, like try as you might, some little thing will go wrong and you won't get awesome images. So you're graded on did you implement a discriminator, a generator, and did you get the training algorithm? And there's like certain things we know that we're looking for. Like you have to implement the gradient penalty, for example. And like we'll know if you didn't do that. Okay? And so yeah, you're not graded on the quality of your images, but I would hope that you would try to make them awesome.
I really liked the line in the Lab 7 spec that was like, you should expect to see reasonable results after 2 to 4 hours of training. Could we have a line like that going forward?
Yeah, we can do that. I think we said here, we trained for a long time to get the really nice images.
Oh, there it is.
It was more like 8 hours. But like I said, it was like 5 minutes and we started seeing some signal. So Shreya would often train for just 2 or 3 hours at a time. And that seemed to get pretty nice but blurry faces. So you should see something pretty fast, then you'll see pretty nice faces after 2 hours, and you should see really pretty good faces after about 8 hours.
How would you, just out of curiosity, this was not Colab, correct?
Yeah, that's right. On the GTX. Yeah. How would that compare on the Colab? I don't know. Yeah. It's the Colabs are like K80s or something, so it's probably similar. But I don't know.
Yeah.
No, shaking your head.
Well, I think we've
No,
tested
your
it.
partner, your neighbor was
Yeah,
shaking
we've
his head.
tested Colab at various times, not just for this class, but, and even though it is like a nice GPU, you don't get all of it,
Right.
is the thing, so, yeah. It seems to do okay, but probably not,
Probably won't be that fast.
yeah.
Okay, yeah.
this is a question kind of on GANs in general. So from what I understand, NVIDIA was able to get really high resolution images, training to create like, I don't know, 4x4 or 2x2 image, and then 16x16 and
Yep.
gradually stepping up. Did they use the exact same weights and then just change the output size, or how exactly did that work?
What you do is you take the network that you've trained at the lower resolution, then you add new layers, but you initialize the parameters of those new layers to represent an identity function. I'm pretty sure that's how they did it. So it just initially just passes straight through and you're left with the same network, but now you have new parameters you can also fiddle with. So,
So a layer to go between like 4x4 and 16x16, and it's just trained to that identity?
let's just initialize to the
Or-
identity.
Yeah,
Okay.
initialize the identity.
Yes. Okay, any questions? You feel confident? Feel okay about this lab? Yeah, go ahead.
How do we go about doing the linear interpolation between the two images?
So what you do is you go ahead and pick two random z values, and then you go ahead and just like linearly interpolate between them. So you get a sequence of z's, and then for each one you run it through the generator, and you should get an image out. By the way, if yeah.
The GAN paper, the DC GAN paper uses odd-sized kernels, 5 by 5, but those don't turn even to even. And all the implementations I found online were using even-sized kernels. So I'm just curious, what's the mismatch
Yeah,
there?
so what we-
is those kernels, it's showing the size after the transpose compilation.
Let's see what we did. We used
Yeah, you have to
So
use
it's
an
the kernel
even-sized
size
kernel.
you
So I'm just
described
curious why the DC GAN paper has odd-sized ones.
I don't
That
know.
doesn't even work.
Yeah, I don't know. So, yeah, I looks like we used two vectors. That's fine. Any other questions? Yeah.
This is more of a conceptual question. Earlier in the semester, we talked about how it's almost always better to use smaller kernels when doing convolution.
Right.
And just to add another convolutional
Yep.
layer, like two 3x3s,
Yep.
use 5 by 5. Is there a particular reason why this one uses 5 by 5 kernels rather than 3x3?
Sorry, you mean the DC GAN, the original DC GAN?
Yeah.
Well,
And
now I'm
it's just
questioning.
published, but
Now I'm questioning myself. So I thought that they used 5 by 5s, based entirely on this image. My guess is this was published in 2015. And I think back then they didn't understand like more smaller convolutions is better. So they probably just got this working and we're happy. So, but I like this because it's not too deep and seems to work pretty well. But you're absolutely welcome to play around with topologies. Once you get everything kind of working, it should be super easy for you to swap out a new generator and do some cool ResNet thing, for
you
example.
could potentially do 3x3 and just double the number of layers.
Yeah, totally.
Supposedly get
Totally.
the same results.
Yep. Okay, good. All right, oh yeah, please.
We probably went over this, where when we calculate the gradient penalty on like an
Yes.
interpolated image, right? We're taking what is it? X hat or X with tilde on top, or one of those is interpolated one where we have the gradient penalty, correct?
Yes,
And in the paper, they use a random value.
epsilon.
And that's, we do the same thing, and that's just to take different samples at different points, not always in the middle, right?
Yes, exactly. Yep, so in Tria's code, she, like, you sort of see here, she just goes ahead and like generates some epsilon and then uses that to like construct X hat, which you then, you know, calculate the gradient of, and then that feeds into the gradient.
Would it matter if that epsilon is normal or uniform?
Epsilon is supposed to be uniform,
That's what I-
according to the paper, because you're trying to linearly interpolate between the data distribution and the generated distribution. Okay, cool. Any other questions? This is great. Okay, keep going, and let me know how it goes. And if you you have questions on Wednesday, or on Piazza, let us know. Okay, so last time we talked about Big GAN, super fascinating paper. Thanks to whoever posted the Twitter feed, by the way. That was a lot of fun to read with the author. I thought that was super fun. So anyway, very fun paper. Today, we are going to talk about autoencoders. So I realized we've used this word before in class, but I don't think I ever taught you what it was. And I thought we should cover this. Plus, it will segue nicely into, so I think we're going to be done with GANs. But we're not done with unsupervised learning. So GANs are just one way to convince a neural net to do unsupervised learning. There are several other ways. So now we're going to begin an exploration of two other main methods. One is called a variational autoencoder, and the other are called reversible flow networks. And so I figured, let's talk about autoencoders, and we'll also talk about variational autoencoders. At least we'll get to the point where we should be able to at least understand what the word variational is and what the word autoencoder is, even if we don't understand what they mean together. Okay, so autoencoders. Very, very simple idea. It looks like a network. It looks like a network with a bottleneck layer. And so the idea of an autoencoder is you have some inputs, say X, and maybe a bias, some sort of bias thing. You feed it through some sort of network and you get an intermediate vector, maybe called Z, and then this is called the encoder, and then you want to take whatever Z is, put it through another network, and get back out the same thing that you put in. Does that make sense? So the X's here are supposed to be the same as the X hats here. So you are encoding yourself in a Z vector, hence the name autoencoder. Okay, that's it. That's the idea of an autoencoder. So there's a couple things though that I think are quite interesting about them that I want to explore with you today in this lecture. So first of all, one thing that's interesting is that there is a relationship between autoencoding and principal components analysis. So if you didn't have any nonlinearities and you tried to do this, so you take your input, try to go through some, say, fully connected layer to some Z vector, and then from Z back through another fully connected layer back to X, you would essentially be doing, other than like trained it using stochastic gradient descent, you would be doing PCA. As soon as you put nonlinearities in here, it's not PCA anymore. But if you don't have any nonlinearities, it actually is exactly equal to PCA. Or at least you recover the same stuff. So that was really interesting. And this idea is really old. It's been around for a long time, back since like the 80s, by Jan LeCun. We've heard from him earlier in the semester. He's now the director of Facebook AI research. What's interesting is, so this has been traditionally used for dimensionality reduction. In other words, I have some input and I have some algorithm that scales maybe badly with dimensions. So if I can somehow squeeze it down to its essence, I can use the Z vector as a representation of my data instead of the original X vector. So I can reduce the dimensionality of my data to just its essence and then plug that into some downstream algorithm. Also useful for feature learning. Interestingly enough, most people don't use this for compression, even though it kind of seems like maybe you could. The reason is you're learning it on a very specific data distribution under Flossie, and there's just not too many times when that's helpful. So, but turns out that this has a strong connection with generative modeling, which is why we now care about it again. Okay, so just a little bit more formally. So you're given some X, so there's no labels here. Given some X, you want to take, so you want to craft some function of X where you go, maybe some linear layer with some biases, you go through some sigmoid, you get a Z vector, and then you want to take that Z vector, plug it through some new weights, new bias, new sigmoid, and get back out your X hat, and then you define your loss function by comparing X to X hat. And typically, you'll do some sort of, could be whatever we want, mean squared error, cross entropy, whatever makes sense. And so you might think, well, this is kind of trivial. And it is. It's actually a very simple idea. But what we'll see is there's some interesting things you can do when you start thinking hard about that Z vector in the middle. And, okay, so training, you can do this. Training, just normal training. Okay, so we need to distinguish between two different types of autoencoders. So there's, hello? I'm going to change my batteries. Okay, well, that was my lecture. Hope you got that. Okay, let's try this again. Hello, computer. Hello. Right. Okay. Okay. Two types of autoencoder structures. There are, so there's ones where the middle z vector is smaller, we'll call that undercomplete, and there's ones where the z vector is bigger, and we'll call that overcomplete. Now, what are the advantages and disadvantages of both of these architectures? Talk to me, give me some ideas, yeah.
The overcomplete one from like the identity function.
Okay, so what do you mean by that? And why is that a problem?
Yeah, like, so there's 6 nodes on the bottom there. So
Yep.
say the left 6 nodes can just copy the input and then copy to the top node.
Okay, yeah, and what would your loss be?
0.
0, it'd be awesome, right? So, okay, so the overcomplete architecture has some problems unless you do something else to convince it to learn something interesting. Because you can just learn a trivial function. Okay, yeah?
But if you did do that something else, it's still possible that it can do a perfect reconstruction, which the undercomplete probably can't.
Right, so we are guaranteed, probably, to lose information over here. Hopefully we'll keep the most important information. We could, in theory, retain all the information, but maybe learn some interesting representation. By the way, I think there was some machine learning intuition back in kind of the 80s and 90s, where people said, they said, well, when you have a machine learning algorithm, you want the most compact representation of your data as possible. We don't want irrelevant features. We don't want superfluous bits floating around. We want to find the essence of the data. And so these sorts of architectures were very popular. But then with the advent of things like kernel machines, people realized, actually what you want is you want lots of features about your data. You want to explode your data into a bigger, more roomy feature space so that your algorithms have an easier time finding the right, say, classification boundary. So it is interesting that these days you have to be very careful when you're doing something like this. Most of the time people actually do something like this with constraints. We'll talk about those in just a second.
You mentioned something called a kernel machine. Can you
Yeah.
speak to that a little bit?
Oh, sorry. This is like kernel learning theory from like support vector machines, kernel regression, kernel recursively squares. Anything that has the word kernel in it. The idea of seriously, there's like this whole like taxonomy of. You can take any linear learning algorithm and kernelize it, and you get, it's kind of cool. You get a linear algorithm in a nonlinear feature space, which gives you essentially a nonlinear algorithm, but with all the properties of a linear algorithm. It's kind of cool. But the idea of a kernel is that it takes your data and explodes it up into a cool feature space, and hopefully makes the linear algorithm's job easier. It's rare, like a linear decision surface is totally fine in a high dimensional space, because you can almost always find it like a separating hyperplane between two classes, as long as you have cool enough features. Yeah, go ahead.
Would a quadrant machine be like a really simple example of a kernel? Like
Sorry.
a quadrant machine?
Quadric?
Is that what that's what it's called, right?
Quadric? Oh, I don't know. I've never heard
So
of that.
if you have like x and y, then you kernelize it to get x squared and y squared. And
Oh, yeah, so that would be one example of a feature. Yeah.
Okay.
So with the example where you're going into smaller dimensions, isn't it more dependent on your parameter space? Like if your parameter space is large enough, you can still get perfect loss.
Potentially, yes. Well, it depends on how close, it depends on how much information is contained in the original space. So if this is, for example, these are images, we know, so think of it this way. Images, natural images, lie on a manifold in a high dimensional space. You can see that because if you just sample random images, you like never see anything like even remotely useful, right? Like it's the space of possible things that look like actual images are vanishingly small. So it's clear that this is like way over parameterized. And as a result, yeah, maybe you can capture the essence of natural images with a smaller way. But for other data sets, that might not be the case. So it really all depends on kind of the distribution of data in the original X space. Okay. Okay, so just so we're clear, so undercomplete layers are smaller. It compresses the data, but only does it well for the training distribution. And then these hidden nodes you can use for all sorts of things, like you can call them features or whatever. By the way, so you might think, so I have an encoder, and I have a decoder, and I have a z-vector. So maybe what I could do is just like sample some z's here, plug them through the decoder half of the autoencoder, and get cool images. That doesn't usually work. Why not? Yeah.
You probably have to be really careful on how you select your z-vector, because it's learned some distribution of z-vectors, and you need to know what that is so you sample properly.
Right, right. And so what I've explained so far is, sorry, Brian's answer was, well, what are you going to sample your z-vector from here? It's not necessarily uniform. It's not necessarily Gaussian. In fact, the network could have learned some crazy distribution. And unless you're sampling from that distribution, you're going to be plugging garbage into your decoder. So that's very different than what we're trying to convince the GANs to do, which is the GANs have to be able to generate a plausible output for anything that we sample from the correct Z distribution, which we've taken to be Gaussian.
This is probably similar to that, but like your decoder in essence is learning your encoder, then you could even connect the weights there.
Yeah, so that's right. These are definitely coupled, right? Your encoder kind of has to, they have to agree on a shared representation. Maybe that's the way to say it. And so the weights are not typically shared, but there's definitely coordination going on. Yeah.
Could that provide some kind of encryption where we compress the stuff using the encoder?
Yeah.
And we have to have the decoder. Okay.
So in theory, why not, right? It's a universal function approximator. Crypto functions are just functions. Could this learn some cool, like, RSA 1024-bit? Maybe. My guess is that an actual cryptographer would tell you that no. But it could be. I think some people have actually tried to do that. I'm not sure though. Yeah.
Would you have to be careful to train your decoder more slowly than your encoder?
No, in this case, you just train it all jointly.
Okay, I just imagine if the encoder suddenly decides to change directions, the decoder will have no clue.
Yeah, I mean, as usual, you just want to take small steps in parameter space. Okay, so let's keep going here. Overcomplete, so quick discussion here. So overcomplete autoencoders, there's no compression now in the hidden layer. And so there's no guarantee that this middle layer is going to extract any sort of meaningful structure. Certainly it's going to be overcomplete in the sense that there's going to be redundant representations of the information, but maybe that's a good thing. For example, the example of a quadratic feature space where you copy some things, but then you add some derivative features, but that makes everybody's life easier. Okay, I will skip this. By the way, you can kind of do latent space interpolation with an autoencoder. So you can imagine encoding 2 digits, getting 2 Z vectors, and then like plugging them into the decoder and getting some latent space interpolation. Totally fine, but again, there's no guarantee that everything in between those 2 Z vectors is going to be a valid Z vector, because we're not placing any constraints on the Z space. Okay. Finally, you can imagine like a convolutional version of this, etc. Okay, we'll skip all this. Yes?
So that looks like exactly like a UNet. Is a UNet
Yeah.
like an autoencoder?
A UNet is kind of like an autoencoder, except it's got those skip connections. So if you didn't have the skip connections, it would be exactly an autoencoder. Yeah. Okay, so here's some examples. So top row is the input, the bottom row is the reconstruction. So you can train these things really fast, and you can try to reconstruct images, things like that. Okay, but let's talk a little bit more about overcompleteness. So we've said if you have an overcomplete autoencoder, that middle layer is not necessarily going to compress in any meaningful way. But maybe we'd still like to have it learn a meaningful representation of the data. So what can we do? And the answer is we somehow impose other constraints on the network. So we have a word for that. It starts with an R and it's on the slide. Regularization. So we're going to regularize that middle layer. There's a couple things we can do. So for example, we can put a sparsity constraint on it. So we can tell that middle layer, okay, middle layer, you can be huge, but I want you to be sparse. So we're going to put maybe an L1 activation regularization term on that hidden layer. And so what that'll do is that'll say, okay, I'm allowed to use all these units, but I have to use them sparsely, and hopefully that'll learn some interesting decomposition of the data. This, by the way, is a bad example. So this is a not sparse hidden layer, which has learned essentially an identity function. Like you can sort of see the structure of the images which have been captured in the hidden layer. A much better sort of representation would be something like a parts-based representation, where that middle layer learns, if we were doing it on digits, for example, learns all the different strokes. And so we know, oh, this digit is some sparse-ish combination of little digity basis functions. And then with the right kind of regularization, we can learn that sort of thing. Okay, that's all we're going to say about that. I want to move on a little bit. There's also this thing called a denoising autoencoder, which is a very simple twist on the idea. So here, we take an input and we add a bunch of noise to it. And then we take that noisy thing, put it through the encoder, get a Z vector, put it through the decoder, and we want to have it produce the denoised output. So, sorry. We want to generate the same thing, but the original, not noisy version. So why would this be useful? What do you think?
Image super resolution, so.
Okay,
Yeah,
it could be
like-
super resolution, yeah.
Yeah, like below your image of cells or something, you get better image quality.
Okay.
Could you just plug this in place of like a common filter or something?
Yeah.
Filter?
Yeah, totally. And what assumptions could you potentially make on the noise distribution here? Does it have to be Gaussian though? No, it could be anything. So if you want some awesome filter, like that's the problem with the Kalman filter, is linear Gaussian. Well, like the world's not Gaussian or linear. Like those are terrible assumptions. So, but here you could put any kind of noise on your image and potentially learn a filter that would denoise it. So yeah, I saw a hand back up here. Yeah.
I was just going to say, I mean, looking at the problem of how do we keep it from learning the identity function, the identity function in this particular case is not what it's going to be trying to train against.
Right.
It learns the essence of true-ness
Yes.
and whatnot.
Yes. So actually adding noise can help us as another form of convincing the network, look, you can't just pass this through as the identity. And you can't rely on any individual like pixel correlations. You have to kind of squint your eyes and learn a little and figure out what was really there and then reconstruct that thing. So yeah, this is actually a very simple way to convince the network to learn a meaningful representation of two-ness. Yeah, go ahead.
Maybe we'll get to this, but we learned about embeddings.
Yep.
Correct?
Yep.
And this seems to be.
Yep, it's an embedding, right?
Yeah, okay. But what we talked about then was sort of a statistical approach to getting good embeddings, where these wouldn't have all the properties that we had before with embeddings, where like you can subtract some feature and add some other feature to get a different thing.
Yeah, maybe they would, but maybe not. Hard to say. There's nothing here that suggests that this latent space is going to be linear and well behaved. Yeah. Yeah, by the way, so this is all, I'm showing you this in the context of images. I've often thought, I don't know if anybody's done this, but I've often thought it would be fun to do the same thing like in the space of words. So you can imagine a denoising autoencoder where you take sentences in and you output cleaned up sentences. So I'm like, ooh, it's like Deep Grammarly or something, like, or like a Twitter to English decoder or something, where you can take just some crazy, like, uninterpretable thing and make it better.
VidAngel.
VidAngel. Yeah, so we're gonna corrupt, corrupt our movie with bad content and then learn to filter it out. You can try that. Yeah, just.
I mean, you actually could do it if you trained it on like,
Actually, you could, yeah, right.
not necessarily like trained on pixels, but like which segments are.
Yeah. Yeah, totally. So anyway, so the point of a denoising autoencoder, I think it's very simple. It's I think it's kind of a clever idea, and I think we basically said all this. So the one thing that is interesting here about, I found this great visualization. So this is, so again, imagine that there's some interesting manifold of our data in the original X space, and our data kind of lies near it. The denoising autoencoder takes one of these images, moves it off the manifold, so it's not on the manifold of clean-looking, nice images, and has to learn a function that will project it back onto this manifold, hopefully as close to orthogonally as possible. So what the network is learning is something about, it's not the tangent space, but it's like what's the space that's